Hi class, this video is the first video in our new unit, Wave Nature of Light, and this is topic D1, Wave Properties, which includes refraction, dispersion, total internal reflection, and a few more. We've got a lot of material to cover here. It's really necessary to have a strong foundation of some of the topics that we learned from grade 10 optics and grade 11 sound and waves. To be really successful in our grade 12 complex problems. So we're going to do a little bit of review before we do each one of these grade 12 topics. So by the end of this first half of the lesson, where we're going to recall the principles of mechanical waves and be able to describe transmission, reflection, refraction, partial reflection, refraction, and understand how those observations can be made for both mechanical waves, such as water waves, and light. This suggests that light follows wave-like behavior. So remember from grade 11 that neighboring molecules are connected by intermolecular forces, which means that a vibration can travel through a material. And a mechanical wave is a transfer of this energy through the medium by means of a disturbance or a vibration. Recall that a mechanical wave, such as a water wave, requires a medium that the energy is transmitted through. So obviously a water wave, the medium is the water. If you send a wave through a slinky, the medium is the slinky. In grade 11, we talked a lot about sound waves. So sound is an example of a mechanical wave. It does require a medium to transfer the energy. So for example, sound has to travel through air or water. But electromagnetic waves, like the light in grade 10, it does not require a medium. And this unit is, we talk about waves in order to better understand light. And there's wave-like behavior of light. But remember, light is an electromagnetic wave, which does not require a medium. So a wave is a transfer of energy from one place to another by means of a disturbance or a vibration. You should be familiar with amplitude, so amplitude, frequency, wavelength, period, crest, and trough. So notice that with period and frequency, I didn't have anything to point to because they are time-based characteristics and you can't really point. If this was a video over time, then they would have sort of a visual meaning. But right now, this is a snapshot. These are the geographic. These are like physical things that we can measure if we take a picture of a snapshot in time, whereas these would have to have a video or know things over time. Period is time and frequency is how many events per unit of time. So with the features of a wave, you should know the definitions. A crest is the point of the maximum or highest displacement on a wave. The trough is the point of minimum or lowest displacement. Amplitude is the distance between equilibrium and a crest, or between equilibrium and a trough. And other features of the wave, we've got wavelength, which is the distance between any 2 points on the wave. The easiest is to measure crest to crest. So like crest or crest, but it's the same as trough to trough. And then period is the time for one complete cycle. And then frequency is the number of complete cycles per second. A wave transports energy, but does not necessarily transport matter. So a wave pulse, like this, carries energy along the string. If let's say you tied the string to the wall and you held the other end and you moved your hand up and then down, you would send a wave pulse. And the direction of the energy transfer is to the right. But the particle, in this case, the particle motion is up and down. Over here we have the same scenario, except there is continuous motion of the person's hand. So a periodic wave, so a wave pulse versus a periodic wave. A periodic wave is a wave with a repeated pattern over time or distance. So we've got two types of mechanical waves: transverse, where particles vibrate perpendicular to the direction of the flow of energy. For example, a pendulum or a guitar string. And then we've got longitudinal waves. So particles vibrate parallel to the direction of the flow of energy, like sound or compression of coils on a slinky. And we must understand these principles in order to suggest which type of wave properties light may exhibit. Sound is an example of longitudinal wave through air. And light is better described as a transverse wave. And we can, when we get to the polarization topic, we'll talk more about this. But note that although light looks more like, it has more in common with a transverse wave, it is an electromagnetic wave. It's actually not a mechanical wave, because an electromechanical wave does not require a medium, and all mechanical waves require a medium. So just another little animation to kind of burn in your memory, or bring up what was burned in your memory about transverse wave or longitudinal wave. So here are the properties of waves that we're going to be talking about in this lesson. Now we've done a little bit of review, and there's even a little bit more coming. So transmission, reflection, refraction, partial reflection and partial refraction, dispersion, and total internal reflection. So maybe these terms are totally familiar to you. There's nothing to remember. We're going to go over most of them with a little bit more depth than you probably have learned last year or grade 10. So when we're talking about transmission of waves, there is a wave front. So the front edge of the wave. So let's say we have a periodic wave. The first, it's like the leading edge, that's the wave front. And then the wave ray represents the direction of the travel. So this would be the wave front, and this would be the wave ray. This might be a rope on a rope tied to the wall, and you are moving one end of it up and down and sending that energy along the length. But this is maybe a cross section of a water wave. So this year we're going to look at the top, the bird's eye view of a water wave. And so if you were looking bird's eye view of the water wave, you could see that there's like crest where it's darker because it's a thicker amount of water that you're trying to look through, and trough where it's like a skinnier amount because it's a thinner amount of water before the bottom of the surface. So you've got crest, trough, crest, trough. We can still measure wavelength, but we can't measure amplitude, but we could still measure wavelength through here. So the spacing from crest to crest would still be the wavelength. So here is the wave front, and then 90 degrees to that is the wave ray. Example of mechanical wave moving from left to right. When a wave is shown from above, the crests are solid lines and the troughs are dotted lines. So this is a convention that's used in this textbook this year. And when we're talking about transmission, notice that we could have a linear source or a point source. So if we had like a puddle of water and we dropped a pencil or a ruler, then it would create this linear wave from the linear source. Let's say if we dropped the pencil, picked it up and dropped it again repeatedly, then it would create these waves. Point source, let's say now we just take the eraser side of the pencil and dip it into the water repeatedly, we'd get circular waves. So this might be what you see if you drop a rock into a pond. So again, the direction that the wave front travels is the direction of the transmission. We have the wave ray, wave ray, which is there, and it's 90 degrees to the wave front. Do you guys remember the universal wave equation? So V equals F lambda, where V is the speed of the wave, F is frequency, lambda is the wavelength. So frequency is how many crests arrive each second, And the speed is how far in meters a point on a wave will travel per second. And then wavelength is the distance between 2 points on a waveform. And notice the units. So wave speed is determined by the medium and the medium properties. Frequency is determined by the wave source. And the reason why it's important to highlight these things, there are going to be a number of proportionality statements, just simply proportionality statements in multiple choice questions, but also as part of bigger questions. So the proportionality statements are really important. So what do I mean by that is, let's say if we hold F constant, because the wave source, actually, let's take a step back. So for example, in grade 11 sound and waves, we have a formula that says the speed of sound and air is based on air temperature. So that's what I mean by speed depends on medium properties. So we have colder air, then the speed is slower. Warmer air, the speed of sound is faster. And then what would the interpretation of frequency be from grade 11 sound and waves? That would be the pitch or tone that is played by a speaker or a tuning fork or a person singing if they could sing a pure pitch. So now going back to what I was saying about the proportionality statement, if F is constant, V is proportional to lambda. So if F is constant, let's say if we have a constant wave source, if speed increases, lambda will increase. So what would be an example when this happens? Let's say, like to keep this left side equals right side, let's say speed were to double, then wavelength would double. So let's say a certain pitch is played and that sound is radiating out of the speaker, and then that sound for some reason travels from cold air to warm air. That would be an example of speed increasing, and then the warm air waves would have also an increased lambda as well. And then you should think of this exercise as well. What happens if V is constant? Then they're inversely proportional between F and lambda. So you should think about the different combinations. For unit analysis, which we should always do, did you notice that the SI unit of frequency is hertz, just like we had last year? It's per second is the meaning of hertz. So that's meters per second, and we do get speed units. So let's try an example. We have a 100 hertz sound traveling with a speed of 343 meters per second, and then that sound changes medium to a new speed of 320 meters per second. Will the frequency of the source change, and what is the wavelength of the sound in each medium? Okay, so will the frequency of the source change? We have this sound wave, and the frequency is not going to change. I guess this is kind of a trick question. So no, the frequency does not change, even though this wave continues in a new medium. And then what is the wavelength of the sound in each medium? Well, we get wavelength through the universal wave equation, V equals F lambda. We have V, we have F, and we can solve for lambda. So we isolate lambda, speed over frequency, and we get 3.43 meters when it's in traveling medium number 1. And then going to a new speed, it will have a new wavelength. So a shorter wavelength would mean that these the wave is more bunched up. So the longer wavelength means it is kind of more spread out horizontally, whereas the shorter wavelength means it's kind of bunched up. And note, this is the same reduction of speed that occurs, like right now we're talking about sound from maybe hot air to cold air. That's the same analogous reduction in speed when water waves travel from deep water to shallow water. So have you noticed that maybe the ripples closer to the shore are kind of like more pronounced and noticeable, whereas it's less noticeable further out? Okay, so the next, so that was that was, what were we talking about? Oh yeah, transmission was number 1. And number 2 is reflection. When a wave reaches a reflective barrier head-on, it is reflected back along its original path. At a fixed end, the reflected wave is inverted. So notice it goes in as a crest, comes out as a trough. At a free end, the reflected wave is not inverted. So it goes in as a crest, comes out as a crest. And this is easily observed in mechanical waves. And the question should always be, well, what about light? So fixed ends are, it is mimicked for light waves with fixed ends when we travel from a less dense medium to a more dense medium. Free ends are also mimicked when we travel from a more dense medium to a less dense medium, and later we'll observe the interference patterns that result from this phenomenon coupled with others. So the fact, what does it really mean when the light is not inverted or inverted? So this is mimicked with light, so we're going to get more in future lessons about why that is important. When a wave reaches a reflective barrier at an angle, it is reflected such that the angle of incidence equals the angle of reflection. This is probably maybe the easiest, most memorable thing from grade 10 optics, be it specular reflection and diffuse reflection. Okay, so now we're gonna go on to number 3, but we just have to review a little bit from grade 10. So recall that refraction is the bending of light as it travels from one medium to another. So let's say this represents one ray of light going from air to water. We draw the normal, we have an incident ray, and it hits the surface at some angle. We call that the angle of incidence. In grade 10, we measured the angle from the incident ray to the normal. And then the light will bend because of a different speed, because of a different optical density. And we get this new angle, which is called the angle of refraction, which is the angle between the refracted ray and the normal. And refraction, oh yeah, theta is often used as that symbol for angle. It's Greek letter theta. And then refraction is the bending of light as it travels from one medium to another. So refraction is caused by the change of speed of the wave from one material to another. So light traveling from air, it travels faster than light traveling in water, so it bends. This is a visual of air, the light in air going faster than the light in water. So for example, when a beam of light travels from air to water, it bends towards the normal because light is slower in water than the air. And so light bends towards the normal when light is slower in the new medium. Light bends away from the normal when light is faster in the new medium. And the incident ray, the refracted ray, and the normal all lie in the same plane. So 2 is kind of obvious, but number 1 is the rules for refraction. And there is a mnemonic device that I created for this. So if you're going into a medium that is faster, then the light is going to bend away. If you're going into a medium that is slower, then you're going to bend towards the normal. So this is, the second medium is faster, you bend away from the normal. The second medium is slower, you bend towards the normal. So FAST is the mnemonic device for remembering that. So here's a diagram that we might have used in grade 10 optics. And it's just showing one light ray. When light travels from material 1 to material 2, it bends away from the normal. So here it bends away. In this diagram, when light travels from material 1 to material 2, it bends towards the normal. So when we bend towards the normal, because of that FAST mnemonic device, we remember that S and T go together. So this is the slower medium, therefore this is the faster medium. Okay, so the third property that we've been reviewing up to is refraction. When a wave crosses a boundary between mediums at an angle other than 90 degrees, it bends into a faster medium away from the normal, into a slower medium, it's towards the normal. So you might notice these diagrams look a bit different. One thing that's really important, so I don't want to forget to say it, refraction is easily observed for mechanical waves as well as light. This is the grade 12 diagram where maybe we have water waves and we're looking at bird's eye view of the water waves. And here we didn't bother to write the dotted line troughs. It's just you see the solid lines are crests. So you can see the wave front is the first white line, and then the wave ray would be 90 degrees to that, so going to the right. And the angle in grade 10 that was important was the angle to the normal, but in grade 12, the way we have this line and then the wave ray is 90 degrees to it, we can actually use the angle between the boundary line and the wave front. And if you could draw a little triangle to prove with similar triangles that that's the same angle. If you drew the wave ray, then it would be, the wave ray diagram would be the same as grade 10. But often we're drawing the wave front. And the reason why we want to draw the wave front, we can actually see what's happening to the wavelength. So you can see how they get more spaced out. When water goes from shallow water to deep water, the wave gets more spread out. We actually get longer wavelength. And when it goes from deep water to shallow water, the waves kind of get bunched up. So why is that? So pause this for a moment and think if you can justify or explain that. So remember the universal wave equation, and I was saying the proportionalities are really important. So the wave frequency was constant from this side and the other. F was constant. And because you were going to a higher speed, if V increases, then wavelength increases. So here we were going to a slower speed, lower V, we have a smaller wavelength. And of course, refraction causes some optical illusions that were discussed 2 years ago in grade 10, like the bent straw illusion. And the result is that objects in water, like fish, are deeper in water than they appear to be. So here, if we have a golden treasure chest, it appears to be not that far down when the apparent depth is not as deep as the true depth. Okay, so we have the index of refraction for when we're comparing how light travels through different materials. The index of refraction is an optical property of that material. It's a material property, and it's the ratio of the speed of light in a vacuum to the speed of light in that medium of interest. And since you've got speed over speed, n is unitless. So n equals c over v. And you might remember last year, so this is one way to calculate n if you needed to calculate n or you needed to rearrange given n. There's another equation from n from grade 10. And it says the index of refraction of the second material is equal to the sine of the incident angle divided by the sine of the refracted angle. But this is actually only true if you start from air or vacuum. So it's not that we were lying to you in grade 10, but we were using a really simplified formula. It was actually Snell's law, where n1 was equal to 1. So we were always starting from air or vacuum in grade 10. But now you can go from water to oil, oil to glass, glass to air, air to glass. So you can, there's any combination of material 1 and material 2 that is now possible now that we're doing this full version. And in grade 12, you're expected to use this full Snell's law version, even if one of the n's was 1. So the simplified equation, we're not going to use very much this year. So Snell's law, if you notice, there's 2 sides of the equation. So everything here is material 1, so the blue. Everything here is for material 2. So the index of refraction for the first material times sine of the angle of incidence equals the index of refraction for the second material times sine of the angle of refraction. And once again, if we had a wave ray, we would do the angle to the normal, just like in grade 10. But often we're going to have these wave front diagrams. So I guess maybe this is the wave ray going this way, and this is the wave front. You can see as it hits this at an angle, we can actually use the angle between the boundary and that wavefront. So we can actually use, it's like a little bit easier to measure the angle this year, even though the diagrams are a little bit more complicated. It's really important to know Snell's law and the universal wave equation. They often are used together in this course. So one way we could put them together is this equation, lambda 1 over lambda 2 equals n2 over n1. So this is not a typo, they are flipped. Yeah, this is just useful based on what you have. If you have wavelengths in medium 1 and medium 2, and you have the index of refraction of one material and you want to find the other one. So just depending on what you're given, this might be useful. And this is kind of where you've put a bunch of them, you put Snell's law together with the universal wave equation, and all of this is if you had like a constant frequency. So you were looking at one wave as it travels from one medium to another, as you would do in refraction. And then N2 over N1, where you're going divided by where you came from, is the absolute index of refraction, which can be used for light passing from air vacuum into a medium. And you'll find those on page 448. So let's try an example. Let's say we have a 538 nanometer laser beam. Now that is the wavelength of that wave, of that light wave. And it's aimed at 1 centimeter thick sheet of glass such that the angle of incidence is 60 degrees and the accepted index of refraction of the air is 1 and the index of refraction of glass is 1.5. Determine the angle of refraction, the wavelength of the light in the glass. So those two things we're going to find. So drawing a diagram, you have this 1 centimeter thick sheet of glass. So the top and the bottom are parallel to each other. And our laser beam is shooting light that is 60 degrees to the normal. So if you're going to draw, I mean, you have to draw a diagram for a problem solving question. I highly encourage you to draw like the single light ray diagram. So even if you were given like a waveform, a wavefront diagram, I would convert that to this. So it's the angle of incidence is the angle to the normal, 60 degrees. We have N1 is 1 and N2 is 1.5. So we're gonna refract towards the normal because you're going into a slower medium, so fast, ST. We're going into a slower medium, so you bend towards the normal. And then when it comes out, it's going into a faster medium, so it's going to bend away from the normal. And in fact, these two are going to be parallel. So we've got N1 sine theta 1 equals N2 sine theta 2. We have everything. We have both indices of refraction and index of, incident angle. And we can solve for the refracted angle. So just make sure you understand and can use the inverse sine button, and we get 35 degrees. And then what's the wavelength of this light? We can use that, we have the original wavelength of the light going in. And what is the wavelength of the light in the glass? So the wavelength of the light coming back out would be the same. So I guess I could have done it the same color because wavelength is color. So they are parallel, they have the same wavelength. But during the inside the glass, we have the ratio between the wavelengths and the ratio between the indices of refraction to solve for the second wavelength. And we get 3.57 times 10 to the minus 7 meters. I forgot to mention nanometers is times 10 to the minus 9. So yeah, this is not quite small enough of a number to want to report it in nanometers. Okay, so now the next property is partial reflection and partial refraction. When a wave reaches a boundary between mediums at an angle, to be honest, I think the plural of mediums is media, but we'll just go with it. So when a wave reaches the boundary between media at an angle, we will often observe that only some of the wave is refracted and some of the wave is reflected. Does this diagram help you think of an example from your life? So maybe you are inside looking out the window. You can see what is outside, but you also see a reflection of yourself. So that's an example of this. And the next property is diffraction. So when a wave encounters an obstacle or an opening, it actually bends. And we will explore this more in a future lesson. Oh, sorry, we're gonna go through a little bit more detail in dispersion and total internal reflection. So you have some diagrams here that hopefully jog your memory of what these are. Maybe this looks like the album cover of famous rock band Pink Floyd's Dark Side of the Moon. It's not the exact one, but it's pretty close to it. So in this half of the lesson, well, it's not quite half, but in this portion of the lesson, we're going to focus on dispersion and solving total internal reflection problems using some of the equations we just learned in this video for this unit. So first, dispersion. Dispersion is the separation of a wave into its component parts according to given characteristics, such as wavelength. So you might notice white light hitting a prism and coming out as a rainbow. It's an example of this. When light passes from one medium to another, partial reflection and refraction can occur, and the wavelength changes based upon the index of refraction for the second medium. So we have bending towards the normal for the slower medium, and then bending away from the normal because it's now fast again. Whatever bending happened here, whatever squishing of that angle happened here, you unsquish it there if these two surfaces are nice and parallel. So notice they're parallel. Okay, we've got a table in your textbook that gives you indices of refraction if you need them. So knowing that wavelength changes, actually, let's go back to that. Okay, so when the speed has changed, remember F is constant. So when speed has changed, wavelength has changed. When wavelength changes, wavelength is the color when you're talking about light. So if we change wavelength of light through this dispersion, we have a different color. So that's how you start with white light and end up with rainbow. So visible light or white light is composed of a spectrum of different colors or wavelengths. And when light passes through a triangular prism, the white light is separated into its component colors: red, orange, yellow, blue, green, blue, violet. And the separation of visible light into colors is called dispersion. According to the universal wave equation, speed depends on frequency and wavelength. When light enters a new medium, there is a new speed. So F is constant and there's a new speed. Since frequency doesn't change, that means, oops, what did I do? The change in speed is due to a change in wavelength or color. So the formal definition here is the dispersion is the separation of wave into its component parts according to given characteristics such as length. Now we get to, angle of deviation. It's the angle between the incident ray and the final outgoing ray. So if this is the incident ray and it's going to continue along that direction, it's like, what's that angle versus that angle compared to the normal? So no, due to the shape of the prism, the light leaving the prism will not be parallel to the incident ray, as was the case when we had a block of glass where the surfaces were parallel, just based on this geometry, like a rectangle. Incident ray and then like the final refracted ray, they are parallel, whereas you don't get that with a triangular prism. So let's try an example. So we've got this interesting shape. It's not equilateral triangle like was shown in the prism in the diagram, But light enters a prism and is refracted as it enters and again as it leaves, as shown in the diagram. So it's refracted as it enters and then again as it leaves. Calculate the angles of refraction for blue light, so if blue light did this, and red light as they travel from air into prism if the angle of incidence is 38 degrees. And we are given the angle of incidence for air, which is 1, and the angle of incidence, the index of refraction for blue light in the prism is 1.47. The index of refraction for the red light in the prism is 1.46. So let's take a look at that problem. So drawing a diagram with a ruler really neatly, ideally also with a protractor. And what do we have? First, we're going to talk about this refraction, the boundary between air and glass. So we've got air and glass. We have everything except for the angle in glass. And so we are going to calculate that the angle of refraction for blue light is 25 degrees. And now we do the same thing for red light, and the only difference is we're going to be substituting in the index of refraction for red light, and it's 25 degrees. And then part B and C, calculate the angle of incidence for the blue light as it travels from the prism back into the air. So that's this step here. Calculate the angle of refraction of the blue light as it travels from the prism into the air. It's traveling the angle of incidence for the blue light as it travels from, so this angle here, we've got this like triangle that I've isolated and separated over here. And you can see using some trig to calculate that angle there. So we've got 55 degrees there. And then the angle of refraction of the blue light, so this angle there, 35.2, sorry, how did we get that? 90 minus 54.8. Let's do that just to make sure. So do you see right here, this green X right here, between the normal and the boundary, that's 90 degrees in that little quadrant there. And that's made up of the theta we just calculated plus the angle that we must use, because remember when we're using Snell's law, we have to use the angle to the normal by definition of the angle. So now that we have that 35.2 degrees, we can substitute it into Snell's law and isolate for theta 2 again, and we get 58 degrees, or actually 57.8 with sig figs. Okay, this is our last topic here. We've got total eternal reflection. It is the effect observed when light enters a more optically dense medium and light is completely reflected. So this is a diagram where you have total internal reflection. So whatever this angle is, it's a special angle and a special combination of medium that the light does not escape. It just bounces, like as if this was the surface of a mirror. So let's say if this is water and this is air, there's two conditions that must be met for this to happen. Angle of incidence must be greater than the critical angle. So theta I is bigger than theta C. And the light must travel from higher to lower optical density. So slow to fast. N1 must be bigger than N2. So criteria 2 should make sense because remember fast, in order to get 90 degrees or past that, so 90 degrees is where the critical point is, you're gonna have to bend away from the normal. You have to bend away from the normal if you're going into a faster medium. So criteria 2 makes sense that this has to be a faster side. And then criteria 1 might make more sense now than it did when you first learned it in grade 10. Now that you have Snell's law, so you can plug in the critical angle into Snell's law and sub in N1 and N2, and you'll find that theta r is 90 degrees. So mathematically, this makes sense now that we're working with Snell's law instead of that babyish simplified version of n equals sine theta over sine theta. So anything bigger than that critical angle, and I mean, if this angle was 90 degrees, there's a slide coming up that will hopefully show it. There's nowhere to go except for back into the medium. Critical angle is the theta I where theta r is 90 degrees. This is really important to know because this year you'll be asked to calculate the critical angle. So take a look at this. If we have a really, we're really close to the normal-ish, then the light's gonna go through. And the further we increase the angle to the normal here, the more angled it's going to be up to some critical angle. So we're going to increase the angle of incidence up to some critical angle where now we're not going out into the air, we're like exactly on the boundary line. Anything past that critical angle, so this one's past the critical angle, you'll go back into the medium and you get total internal reflection. So we solve for critical angle using Snell's law and using theta 2 equals 90 degrees and solving for theta 1. So what is the incident angle where the refracted line will be 90 degrees or on the boundary? Okay, let's try an example of that, the last example. So we calculate the critical angle for light passing through Pyrex glass into air. So first thing is, you'll need the indices of refraction, which means you'll need to know what you're going from and into. So we look up our indices of refraction. So those are our givens, 1.47 and 1.0003. We draw a little diagram. I always draw the light coming from the bottom with the total internal reflection questions because, or sorry, the critical angle questions, because I think of like if I was scuba diving and I was looking up at the boundary between water and air. Actually, let me show you. Okay, so I think of this picture. This picture helps me get a really good visual. If I was scuba diving and I was looking straight up in this to the sky, straight up, I would see maybe sun and clouds. But if I look at an angle, like upwards at the water, I see the reflection as if this surface looks like a mirror. Do you see how like you see the mirror as if it was the turtle as if there was a mirror? So that's my visual. So I always think of water and air example, and I'm in the water looking up at the boundary. So that's why I always draw my diagrams in that way. Oops. See, I told you it was the last example. Okay, so in this example, you just used Snell's law, but seeing critical angle, you need to know that means that theta 2 is 90, and sine of 90 is just 1, so it's really just the ratio of the indices of refraction. And in this case, make sure you do sine inverse of the ratio of the indices of refraction, then you get 42.9, and for proper sig figs, I guess it would be 42.9 degrees. Okay, so that's all the properties we're going to talk about today. It's really important to do these practice questions because there's all these variations of questions that you've seen before taken to the grade 12 level, and it's a really important foundation for the stuff that's coming up next. So make sure you do these practice questions and submit them, and make sure you do the exit ticket for this video, and have a great day.